This video is on half-activity and decay constant. Question number 1, define half-life units. Half-life is the time for the activity of radioactive substance to decrease by half. Half-life is a time in which half the number of unstable nuclei decay. So I just told you the meaning of half-life. So now your next question is, what is activity? So activity is a rate of decay. The equation is number of decays per second, which is 1 over seconds, which is equal to becquerel. The units of becquerel are not equal to the units hertz, even though they both have the same fundamental units of 1 over second. So an activity versus time graph looks like this. So you have activity as the dependent and time as the independent. And you see this rectangular box here on the left, that's 1 half-life. Then the second box, that's 2 half-lives. Then the third box, which is the smallest, that's 3 half-lives. Question 3, complete the following sentences. After 1 half-life, the activity of the radioactive sample will decrease to half the original activity. After 2 half-lives, the activity of the radioactive sample will reduce to 1/2 times 1/2, which is 1/4 the original activity. And after 3 half-lives, the activity of the radioactive sample decreases to 1/2 times 1/2 times 1/2, which is 1/8 of the original activity. Question 4, define count rate units. Count rate is the number of nuclear radiation events detected in a given time. The units are 1 over seconds or 1 over minutes. So the units are not hertz, once again. Question 5, define background radiation. It's radiation from other sources you are measuring. This can come from the ground, rocks, and out of space. So compare the terms background radiation with background noise. Maybe you'll never measure zero background noise no matter where you go or how hard you try. Similarly, you may never measure zero background radiation. I mean, there's electromagnetic waves coming from space to the Earth, right? Question 6, why do stable nuclei have more neutrons than protons? From Coulomb's law, protons repel protons because they have the same charge. In the nucleus, the neutrons are between the protons and act as a barrier to keep the protons apart from each other in the nucleus of the atom. Question 7, what is the ratio of neutrons to protons for stable nuclei? If Z is less than 20, then the neutron to proton ratio is about 1. This increases to about 1.52 for larger nuclei. Recall that Z is the proton number or the atomic number. Question 8, circle the correct answer. Alpha particles leave the nucleus with discrete energy levels. Question 9, beta minus particles leave the nucleus with continuous energy levels. Question 10, beta plus particles leave the nucleus with continuous energy levels. And finally, question 11, gamma rays leave the nucleus with discrete energy levels. Question 12, what is the meaning of units of the decay constant lambda? Lambda is equal to the decay constant, which has units of 1 over seconds. It tells us the number of disintegrations per second of a radioactive sample. It's inversely proportional to the half-life. If decay constant is large, then the half-life is short. If decay constant is small, then half-life is long. The decay constant approximates the probability of decay in unit time only in the limit of sufficiently small lambda t. Question 13. Describe and define the variables in the radioactive decay law equation. N equals n sub 0 e to the minus lambda t. So n as a function of t is the number of radioactive nuclei remaining. N sub 0 is the initial number of radioactive nuclei. Lambda is the decay constant in time. T is in seconds. So you see lambda t has no units, which is good because e to the minus lambda t, the minus lambda t should have no units. So time is on the horizontal, n as a function of t is on the vertical. Question 14. What is the meaning in units for activity A? Describe and define the variables in the equation. A equals lambda n equals lambda n sub 0 e to the minus lambda t. Activity A is the rate of decay. The units of the activity A is disintegrations per second, or 1 over seconds, or becquerels, BQ. Once again, lambda is a decay constant, n sub 0 is an initial number of radioactive particles. The initial activity A sub 0 is lambda n sub 0. So now A as a function of t is equal to A sub 0 e to the minus lambda t, which is equal to lambda n sub 0 e to the minus lambda t. This should say minus lambda t. The t didn't save, unfortunately. Question 5. State the relationship between the half-life and the decay constant. The half-life is equal to the natural log of 2 divided by lambda, which is equal to 0.693 over lambda. Question 16. Cobalt-60 has a half-life of 5.271 years. Suppose you have a sample of cobalt-60 which has a mass of 25 grams. How many atoms will the sample contain? So I did the unit conversion here. Everything in the parentheses with the fraction, these two that I highlighted, these two are equal to the number 1 because the numerator is equal to the denominator. So 1 mole of cobalt-60 has 60 grams, and 6.022 times 10 to the 23 atoms is 1 mole. Part B, what is the decay constant for this isotope in decays per second? Got to convert time to seconds. Part C, what will be the initial activity of the sample? Here you go. So lambda is from part B. N sub 0 is from part A. Part D, how many atoms of the sample will remain after 3 years? First, we got to find out how many seconds are in 3 years. And then we're going to use this equation. N as a function of t. Part E, what will be the activity of the sample after 3 years? Well, this is the activity equation. Let's just rewrite it A as a function of t, because that makes more sense. It's a function of t. You plug in all the variables and you get an answer. Part F, how many grams of radioactive cobalt-60 will remain after 3 years? This is what we get. Question 17, strontium-90 has a half-life of 28.8 years. Suppose that you have a sample of strontium-90, which has a mass of 45.5 grams. Part A, how many atoms will the sample initially contain? Here's your answer. Part B, what will be the decay constant of this isotope in decays per second? Here's your answer. Part C, what will be the initial activity of the sample? Here's your answer. Part 4, how many radioactive atoms of this isotope will remain after 100 years? So first we got to find out how many seconds are in 100 years, and then we're going to use this equation. Part E, what will be the activity of the sample after 100 years? Here's your answer. Part F, how many grams of strontium-90 will remain after 100 years? Here's your answer. Question 18, the graph below plots the activity of a radioactive sample as a function of time. So initially we had 5,000 atoms, particles, and then it keeps going down. Okay. Part A, what is the half-life of this radioactive sample? Well, when did we go from 5,000 to 2,500? That's 100 seconds. Part B, what is the decay constant of this isotope? Here you go. Part C, how many atoms were initially present in this sample? Okay, so bam, we get 5,000, which is exactly what we see in the graph, right? So n sub 0 is 7.21 times 10 to the 5 atoms. Because we're trying to solve for n sub 0. Part D, what will be the activity of the sample after 10 minutes? We use this equation. Part E, how long will it take for the activity of the sample to drop to 1% of its initial value? So A final is 0.01, right? So that's where we have 0.01. That's 1%. Okay. And then we just solve for T. Part F, how many radioactive atoms will remain after 10 minutes? Here's your answer. Part G, how many radioactive atoms will have decayed during the first 5 minutes? So here's your answer. It's the total number of atoms at 0 seconds minus the total number of atoms at 300 seconds.